Hello and welcome to the first video in the D1 chapter Graphs and Networks. A little starter on the screen if you'd like to give this a go. One of these is impossible to draw without lifting your pencil off the paper or repeating lines. Which one? You might have seen this before. One of these is quite easy, one is a little bit more difficult, and one is simply impossible. The one on the right is the easy one. If I quickly do any old one, we can start here, go around the box, and the triangle, part of the X, the other triangle, finish the X. There we go. The middle one is more difficult. If you start at one of the bottom two corners, however, it is possible. If you started anywhere else, you wouldn't be able to do it. The one on the left is impossible. It doesn't matter where you start, you can start anywhere you like. You are not going to be able to finish this without taking your pen off the paper or repeating a line. That might seem like a strange introduction, but the reason why that one on the left is impossible comes into one of the chapters later. So I'm going to introduce the idea of graphs in a D1 context, networks, and just lots of terminology. There are a lot of new words in this chapter, but you've got to know them because they get used time and again throughout the rest of the module. Most of the module is algorithms, and most of that is algorithms on graphs and networks. Jumping straight in, a graph in this context is defined as vertices or nodes, basically just points, connected by edges or arcs, lines. So a graph looks like this in D1. This is a graph because we have vertices and we have edges. Some of them are connected, some are not, that's fine. This is a graph. A network is very similar. It's something called a weighted graph. Now you might see this word or you might see this phrase. And it's just a graph, it's the same thing, but with numbers on the edges, representing something, whether that's time or distance, whatever it is. But you've got to be a little bit careful here because intuitively, a lot of people would think BF should be the biggest value. But keep in the back of your mind that the graphs in this module do not necessarily represent a physical distance, and even where they do represent a physical distance, the diagram is not necessarily representative of that distance. So it might just be that the vertices are here and here for ease of drawing these two lines, and in reality B and F might be very close. So don't expect the numbers and the relative lengths of the lines to match. So, as mentioned, there's a lot of terminology in this chapter, but graphs are used for most of the module, so it's important that you're familiar with it, and you might be required to define keywords in the exam. Graphs can be connected or not connected. Connected means all of the vertices are connected. So the graph I've got on the screen here, this graph is not connected. If I add a line here between C and D, now this is an example of a connected graph. A graph can be simple or not simple. What I've got on the screen here is simple. Simple means that there are no loops. That's another key term. That means that an edge starts and finishes at the same vertex. It also means that there are no double edges. Here I've got two edges connecting B and C. Either one of these things would make a graph not simple. A graph can also be directed or not directed. Now this actually has another term. Sometimes these are called digraphs, if they are directed graphs. They contract those two words into one. What a digraph is, or a directed graph, means that you've got little arrows. It's kind of like a one-way system. You can travel from A to F, that's fine, but you can't travel from F to A. So this is now a digraph. If I take that off again, this is not a directed graph. These are basic descriptors of the overall graph. And graphs have a vertex set. That's just simply a list of the vertices. Here we've got A, B, C, D, E, F, and an edge set. So here we've got AF, AC, we've got BC, BF, and EF. A graph will also have multiple subgraphs. Now a subgraph is any graph that you can kind of pull out of the one that's already on the screen, or another way of thinking of it, if you delete any element and leave the rest. So if I took D away here, the graph that would be left would be considered a subgraph of this one. Or if I deleted AF and FE, this would be a subgraph. We've got ACB, and you can see this graph here on the original. So any sort of subset of the original vertices and edges is called a subgraph. Zooming in a little bit onto one vertex, we have something called the valency, or degree, or order. There's three words here that mean the same thing. You need to know each of those. And that's the number of edges connected to that vertex. So vertex A here has a degree of 2, because there are 2 edges connected. C also has a degree of 2, D has 0, and E has just 1. F has 3, and B has 2. In all undirected graphs, the sum of the degrees of all the vertices, if you add all of those together, we've got 2 here, 2 here, 2 here, that's 6, and then 7, 8, 9, 10. So the sum of all the degrees in this graph is 10. Now that must be equal to twice the number of edges. That means we've got 5 edges. 1, 2, 3, 4, 5. That's because every edge obviously has a start and a finish. So if we consider AC, that's contributing an order here on A and one here on C, and any edge will always contribute orders in pairs, one on each end. What this means is you'll always have an even number of total valency in your graph. For that always to be true, anytime you have an odd vertice, what that means is a vertex of odd degree. So for example, F here has 3, that's an odd number, so F is an odd vertex. The number of odd vertices in your graph must be an even number. If you had an odd number of odd vertices, you would not have an even number overall. And that's impossible because that number must be 2 times the number of edges, and 2 times any whole number must be an even number. So whenever you have an odd vertex appearing in a graph, there will be another one somewhere, because they will always kind of pair up. So here we've got 3, here we've got a 1, all the others are even, and I guess in this case 0 is being considered to be even. This statement here, concluding that there must be an even number of odd vertices, is called Euler's handshaking lemma. Lemma is kind of like a theorem, but not as serious. It's sort of a mini theorem that you use to prove other theorems. Okay, that's sort of an overview of terms for the graphs. Now let's get a little bit more specific when we look at a single graph and talk about roots, because a type of root in a graph can get very specific. A walk is the most general of any root. So it's just taking any vertex and going to any other vertex in any way you like. So if I start at A and I finish at, I don't know, E, let's say, I can go from A to F to B to C to D to E, or I can go from A to D to E, or I can go A to D to C to A to D to E. I can do anything I like, so long as I get from A to E, that's called a walk. But then a trail is a walk that does not use any edge more than once. So here I think I did A, D, C, A, D, E. That's not a trail because I used A to D twice. But if I just went A, D, E, that would be a trail. And if I went A, D, C, A, F, E, that would still be a trail, even though I used the vertex A twice because I didn't use any edge twice. But if I were to have a path, that would not be okay, because a path is a walk that does not use any vertex more than once. So going from here back to A to come across again to E would not be a path. A, D, E, however, is still a path. And if I went A, F, B, C, D, E, that would still be a path as well. A cycle is kind of what you would expect, is a walk that finishes where it starts. So if I go from A to D to E to F and back to A. But it's a little bit more specific. It's not allowed to use any other vertex more than once. So it's kind of like a path in that you're not allowed to return to a vertex except for the final one, which is why it isn't really a path, because you do use one vertex more than once, but it's only allowed to be that one. I wish I could say we're finished, but there's still more to come. We're going to go a little bit more specific on a cycle and a trail, because there's a specific type of cycle and trail that you need to be aware of. So first of all, the cycle. We just said that's a walk that finishes at its starting vertex and doesn't use any other vertex more than once. But if you are able to do that and use every vertex in the graph, then that's called a Hamiltonian cycle. Now be aware that is not always possible, although to be fair, a cycle is not always possible either. So if I were able to cycle around using every vertex once, in this case, if I start at F, I can go E, D, A, C, B, and back to F. I've used every vertex, and the only one I used more than once was the one I started with. That's a Hamiltonian cycle. Now the other specific one is also called a cycle. It's very annoying because it isn't actually a cycle. So if you have an Eulerian cycle, it's not really a true cycle, it's a trail, and it uses every edge and finishes where it starts. I think that's why it's considered a cycle. It finishes where it starts, but it's not a true cycle because in order to use every edge, you might have to visit the same vertex more than once. And that's okay in an Eulerian cycle, which is why it's not really a true cycle. On the graph shown, I don't think you can. Not always possible, but these are two specific ones that you need to be aware of. I'm going to stop there for the terminology on this video. There is more to come, but let's have a look at a couple of examples. Draw two possible subgraphs for this graph. This is really easy. It hasn't been very specific. I could choose something really simple like AF. There's a subgraph for this graph. Let's do one a little bit more interesting. AE, C, D, and let's connect that as well. There we go. There is another subgraph for the graph shown. Starting at C, write down a possible Hamiltonian cycle. A Hamiltonian cycle is a true cycle, which means we have to finish where we start. We can't use any vertex more than once, but a Hamiltonian cycle means we must use every vertex. So this is quite an easy one because you can go around the outside edge and C is in the middle. So if we start at C and go to E, F, A, B, D, and back to C. In this case, there are quite a few different ones, so long as you don't go along AE, because then you cut out the possibility of going to F without revisiting one point you've already been to. So here, C, E, F, A, B, D, C, and that's how you can write a cycle just as a list of letters. Sometimes you might see them with little dashes in between, but that just takes up a bit of time, especially if it's a long list of letters. Here we've got a network or a weighted graph. The weights are distances in kilometers. Determine the shortest path from F to D. Later in the module we get to algorithms that will do this, but on a simple graph like this we can just do it by inspection. So starting at F, finishing at D, if the lengths were representing actual distances, obviously I would just do that. That's probably going to be the shortest, but it isn't here because of this 8. That's quite big. It would be shorter in terms of the weights to go up to A and down to E, because that would just be a 7. And then going from here to here, again that's 7 direct, but this is a 2 and a 3, that's only 5. So 3, 4, 2, 3 would be much shorter than 8, 7. Other options, if I went up to 3 and then along 7, that's already bigger than the 4 and the 2, and then this 5 is bigger than the 3, so I can see quite clearly now that F, A, E, C, D is the shortest route from F to D. It didn't ask me for the actual weight of that, it just wanted the path. There is the path. We're finished. Find the sum of the valencies of the vertices in this graph. Verify your answer is twice the number of edges. Okay, let me quickly list. A has got 3, B has got 3, C has also got 3, so has D, E has got 4, and F has got 2. If I add these together, that gives me 18. So the number of edges, I know now should be 9, but let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. If it were a more complex graph, you would want to do that systematically perhaps, but we've got 9 there. 9 times 2 is equal to 18. Verified. No doubt understanding it was very easy, but learning it, remembering it, recalling it, using it to define the terms in an exam, that will all take time, and by using these terms throughout the rest of the module, you'll develop that by default. You can have some practice at doing that with questions from exercise 2A and 2B, and maybe I'll see you for some special graphs and even more terminology in the next video.